Our solar system has a new interstellar visitor, 3I/Atlas. Discovered on July 1st by NASA's Atlas telescope, its high speed means it won't be captured by the sun's gravity, confirming it as our third interstellar guest. We have one chance to observe Atlas before it leaves our solar system forever, making every new observation crucial amidst ongoing speculation. 3I/Atlas is the third object from interstellar space, following Oumuamua and Borisov. It boasts an enormous speed of 60 kilometers per second and entered the solar system plane at a very low angle of about 5 degrees. Estimated to be about 7 billion years old, this object is a cosmic fossil from the early days of our galaxy, making it a prime target for telescopes. When discovered, Atlas had a low brightness of magnitude 18. The Hubble Space Telescope captured clear early photos on July 21st, showing it 450 million kilometers from us. These photos revealed ices on Atlas's nucleus sublimating into gas, creating a typical coma structure. This activity, far from the Sun, suggested Atlas contained extremely volatile compounds. James Webb Space Telescope observations confirmed abundant carbon dioxide and a small amount of water, showing the highest carbon dioxide to water ratio observed in a comet to date. Observations continued, showing a slowly growing tail. However, a comet is most active at Perihelion, its closest point to the Sun, where solar effects intensify, vaporizing volatiles and increasing brightness. 3I/Atlas's Perihelion on October 29th coincided with it being behind the Sun from our perspective, leading to mistaken claims of it passing completely behind the Sun. On October 21st, Atlas was in solar conjunction, appearing very close to the Sun in the sky, making Earth-based observation difficult due to the Sun's brightness. Coronagraphs, which block the Sun's light, are used for such problems. However, Atlas's 2-degree separation from the Sun on October 21st was an observational dead zone even for them. Despite Earth-based challenges, space satellites like SOHO and Stereo-A still had suitable angles to observe 3I/Atlas during solar conjunction. As Atlas approached Perihelion, it brightened 3 times faster than expected, undergoing a noticeable outburst. LSST and stereo data showed it brightened by several magnitudes in less than a week. This outburst likely resulted from water ice sublimation and the sudden escape of previously frozen volatile gases. Its ancient, interstellar origin suggests a unique nucleus composition. Such sudden phase changes can cause outbursts, rapidly flinging surface material and increasing gas and dust production, leading to dramatic brightness increases and extra acceleration. The fact that 3I/Atlas shows unexpected, unusual features compared to ordinary comets is actually something we expect, as it's only the third known object from outside our solar system. Color photometry from SOHO's LSST C3 camera showed 3I/Atlas shifted from reddish tones toward blue during its brightening. This indicates which substances are evaporating. If comets turn red due to increased dust, Atlas turning blue means dust production isn't dominant. Instead, it started to outgas. This indicates a different internal chemistry. Comets are like dirty snowballs, containing ice, dust, rock, and frozen gases. As they approach the Sun, these gases vaporize, forming a coma. If dust dominates, a comet appears reddish or yellowish. If gas dominates, especially with molecules like cyanogen or carbon monoxide, a bluish-green glow appears. The blue tones in SOHO images of 3I/Atlas meant frozen gases became active, contributing more to its total brightness. This isn't a true color change, but a shift in material dominance. After news of brightening and color change, the MeerKAT radio telescope detected radio signals from Atlas identified as hydroxyl molecules. Hydroxyl radicals are produced when water ice is broken apart by sunlight, confirming water ice sublimation. This signal confirms Atlas's cometary nature, not an intelligent source. Since its discovery, Atlas's tail structure has been debated. A November 6th photo showed a coma but no large tail. However, photos after November 10th clearly showed the typical ion tail structure, stretching opposite the Sun, formed by ionized particles. We couldn't see the tail earlier because, during perihelion, Atlas aligned such that its tail remained directly behind the object from our vantage point. After November 10th, as Atlas's angle relative to Earth changed, the tail became visible. Strengthening ionization after perihelion also played a role. A November 11th photo by Ajite Kayali revealed an antitail, a structure extending toward the Sun, formed by dust particles spread along the orbital plane. This antitail is a matter of perspective. The material isn't truly flowing toward the Sun. It's observed when we view the dust layer edge-on. Satoru Murata's November 16th photo, combining 24 exposures, beautifully captured both the antitail and the ion tail simultaneously. On November 17th, Francois Kugel's photo showed the ion tail, antitail, and multiple jet flows erupting from active regions of the nucleus. Despite baseless claims, new observations confirm 3I/Atlas is clearly a comet, not a spacecraft. Our work with Atlas continues as it makes its closest approach to Earth on December 19th, passing at about 270 million kilometers. Even at this distance, we anticipate clearer photos. 3I/Atlas, older than our solar system, is exciting enough just by being here after billions of years.